Okay, so the population of Marion, I'm just going to kind of make up a graph here, but let's say that we'll kind of put the years down here and population on the Y. Let's say we'll start about 1883 when Marion was somewhat founded and around that time. And let's say Marion, I would guess, grew. At some point it kind of peaked out. It has been somewhat dropping. And we're probably, I'm wondering, see, when was the peak was probably what? Maybe 1950s or so. Anyway, what can we look at this and tell by this graph? Well, if we want to find, let's say in this, right, so let's say right here is 2016. Well, maybe I want to find the rate of change of the population, right? How fast is the population decreasing? I'm trying to make some predictions, right? Because this is good planning here. You try to predict how big will the school be in 20 or 30 years? How much businesses do we need? All types of predictions. What will the tax bases look like? All those types of things. So if I want to find the rate of change of the population, what am I looking for? What is it about that graph? I want to find the what? The slope, right. I want to find the slope. So I need the slope. And of course, that means that if I have a function for this, so this is, let's say this is my population function, p of x equals something, right? Then the slope would equal to the derivative, right, of the population function for the year 2016. And, of course, it's not just population, but it's all types of things we can find this rates of change of. And it's very, very useful in all types of problems to solve. And so, so often we try to put a function to this, and then we can do all types of analysis on what's happening with that function. But one of the main things what we do in this section is the physics examples. And so let's talk about a little about calculus and physics. So as we may have talked a little bit about, Isaac Newton developed the calculus to solve some questions he had in physics. And so really, the two are very much connected and work very well for both. And so, let's try to make some of those connections. Okay, first one is position and velocity. Okay, so if we have a position time graph, so we have some object, or let's put time on the x. And we have this position, and usually in math we usually use an S for position. That's just kind of been the standard for a long time. Not so much in physics. Often in physics we use either an x or y depending on what dimension we're looking at. Horizontal, vertical. But often in physics we have an s. So this will be s of t, my position. And let's say that here's the position of my object. There's some graph. And, well, of course, if I want to find, let's say if I want to look at this graph, and so at some time t, if I look here, I want to find the rate of change of position. Let's see. The rate of change, right? Well, that would be the slope. And the slope of this graph, right, would be the slope, of course, is a change in y over change in x. So my change in y would be the change of the position. And the change in x would be in time. So this ratio of the change in position or change in time has a special name, which is the what? How fast your position is changing, we call that your velocity. So this is equal to velocity. So the slope of position, right, is equal to velocity, which in fact simply means then that the velocity function can be found by taking the derivative of the position function. So it's a very, very important, put a big box around that. Very, very important thing to remember. If I want to find a velocity function, I take the derivative of the position function. Then, as you can imagine, we're going to make one more connection like this, and that is between velocity and acceleration. And if we think of it the same way, if we think let's have a velocity time graph. So again, I got time always on the x. And then my velocity function is the y. And there's my graph. Well, again, I think about the slope of this graph. If I have some point and some tangent line here. Slope here is change in y over change in x. Well, in this case, the change in y would be the change in velocity. And the change in x would be a change in time. But what do we call this ratio as change in velocity per change in time? Of course, as you can guess, that's the acceleration. Which leads me to my next major thing, and that is that the acceleration function is the derivative of the velocity function. So look, that gives a very nice connection now, because if you have the position function, then you can easily find the velocity function, and you can find the acceleration function. Okay, so that's all connected. All right, so let's use this to solve a couple problems. Okay, so some examples. So on this first one, when we're given the position function of a projectile, and you're given this, and nothing you would be expected to know from, although if you've had physics, it's from physics. S of t is negative 16 t squared v sub 0 t plus s of 0. And again, talk about the notation, because mathematicians and physicists often use different notation. It's just something you have to get used to. There is no set way. We already said, what's the S going to stand for? This is the position. And of course it's at time t. And then some other different notations. What do you think V sub 0 stands for? Yeah, V would be velocity, and the subscript 0 just means at time 0. Okay, so this would be the initial velocity. That's how we, in mathematics, mathematicians tend to do this. Again, we use this a little bit of, I think in our physics textbook they use a VI. That may be very common to use a V subscript I for initial. What would be S subscript 0? The initial position. Alright, so if we give it some information, we can come up with this formula, and then we can do all kinds of things, some analysis of that. So, some questions about this then. So a rock is dropped, not thrown, it's dropped from the top of a building which is very tall, which is 1,600 feet tall. Very tall by Kansas standards, right? So, first question, find the position and velocity functions. Okay. So position function, right? We just need to fill in our variables. S of t equals, let's read this off, so it's negative 16 t squared plus What's v sub 0 going to be? It's 0, right? I'm dropping it. That's dropped. So that means that's 0 t. Now what's s of 0? 1600. Which means then simply my position function is negative 16t squared plus 1600. What about the velocity function? Well, we know that is the derivative of the position, right? So, let's see. In this negative 16t squared, negative 16 would be a coefficient, right? So it's negative 16 times the derivative of t squared, which would be 2t to the n minus 1 or 1. Plus, what's the derivative of 1600? And 1600 is just a constant, right? The derivative of a constant is 0. So in fact, my velocity function then is negative 32t. I mean v of t. Okay, there's question 1. Got those two functions. Well, we could have, I guess I could have asked, maybe we should have added that, I guess it's not on here. How about the acceleration function? What would the acceleration function be? That's easy to find. We know that a of t is the derivative of v of t, which would be what? Negative 32. So in fact, we got that. And in fact, if you've had physics, no surprise that the acceleration of gravity is a constant, right? There's no variable in this, it's a constant number. It's always negative 32. And in the English system, it's negative 32 feet per second per second. So there's all of our functions we need. Okay, question 2 on this. Determine the average velocity from t equals 1 to t equals 2. Alright, now this question, again back to a little bit of physics, makes you review a little bit that it says average velocity, not just the velocity. So this is different. This velocity function actually gives what's called the instantaneous velocity. At that time t, what is the velocity at that instant? But to find the average velocity, we need to kind of remember what the average velocity formula is. So velocity average would be the, I guess we could say, displacement over time, or total displacement, change in time. Right, it's how far did the rock move in that particular time. So how do I find this displacement here? How do I find how far it fell? Between 2 and 1 seconds. Well, I can find its position at 2 seconds. S of 2, right? That's what's at 2 seconds minus S of 1. That makes sense? You know, in physics, if we're doing one-dimensional physics, we say that the displacement is delta x, and that's xf minus xi, right? The final position minus initial position. That's what we're doing here. What's my change in time going to be? My time went from 1 to 2, right? So that's just going to be 2 minus 1. So, now it's time to do the calculation. S of 2, well again I know that this is my function for position. So this will simply be negative 16 times 2 squared plus 1600. That quantity minus S of 1, which would be negative 16 times 1 squared plus 1600. And that's all divided by 1. Alright, let's see if we can do this. So 2 squared would be 4 times negative 16. So it's going to be negative 64 plus 1600. Now if I distribute this through, what do I get here? Negative times the negative 16 would be plus 16 minus 1600. So actually this isn't too bad, right? Because this cancels out, and negative 64 plus 16 is negative 48. Now, does the negative make sense in this case? In fact, it does, because which way is this rock falling down? So that just says the direction, right? The negative is the direction. So it's negative because we've got the rock going down. So this gives me a direction. Alright, so there's the average velocity. Alright, next question. Number 3. Okay, on 3 I want to find the instantaneous. At t equals 1 and t equals 2 seconds. So what is this asking us to find? Yeah, we know that the velocity function, right, v of t, is negative 32t. That finds the instantaneous at any time t we want. So v of 1 at 1 second, right, v of 1 would simply be negative 32 feet per second. And then v of 2 feet per second, right? And the reason I ask this question is to really make us think about this, that the instantaneous and the average are different, which you'd expect, right? Because this thing's accelerating down at 32 feet per second. That should make sense here too, right? That there should be 32 feet per second difference on these, because in each second it speeds up at 32 feet per second. All right, one last question on this. Number 4. I want to find the velocity of the rock at impact. To answer this question, we knowing the velocity function, what do I have to find the velocity at impact? What's the velocity function dependent on? Right? There's my velocity function. What do I have to have? I have to have time, right? I have to find the time it takes it to hit the ground. So you must find time, t. Bless you. Okay, well, we have to use what we know about this. We know that we have this big, tall building. Lots of windows, because how high is this building? We know that it's 1,600 feet. And there is a rock that's just falling straight down. Okay, well, how, I guess as you think about this, it's like in physics, how can I use this 1,600 feet to help me find time? Because when the rock hits the ground, what do we know about the rock? What information do we know about the rock? Well, right before it hits the ground, we know its position, actually. At this point, here's the hitting the ground right there. What is this position? Yeah, S of t has to be 0. It's on the ground. Now, we determined way back on this problem that S of t was in fact negative 16t squared plus 1,600.